When an AI makes a mistake, something remarkable happens. Watch. Data flows forward through the network, layer by layer, producing a prediction at the output. But this prediction is wrong. And now, an error signal races backward through billions of connections. Every single connection learns exactly how much it contributed to the failure. The algorithm that makes this possible is called backpropagation, and it is nothing more than calculus's chain rule, organized in the most ingenious way. Before we can understand backpropagation, we need one key idea: the computation graph. Every calculation inside a neural network can be broken down into a graph of tiny, simple operations. Let's start with the simplest possible example. The function f of x equals x squared. We feed in x equals 3. The squaring operation runs, and out comes y equals 9. That's it. Input, operation, output. This is a computation graph. Each node holds a value, and each arrow represents an operation. Now let's add a second input. The function f of x, y equals x times y. Two inputs feed into a single multiplication node. We set x equals 2 and y equals 5. The multiply operation runs, and the output is 10. No matter how complex a neural network gets, every calculation can be drawn as a graph like this. Simple nodes connected by arrows. And this structure is exactly what makes backpropagation possible. Now let's trace a forward pass through a slightly more complex graph. Our function is f of x, y, z equals x plus y times z. Two additions feed into a multiplication, which produces the final output. We set x equals 2, y equals 3, and z equals 4. First, the addition node computes x plus y, 2 plus 3 equals 5. We'll call this intermediate value a. Next, the multiplication node takes a and multiplies it by z. 5 times 4 equals 20. And that's the forward pass, simply computing values from left to right, input to output. A single forward pass through GPT involves roughly 200 billion of these tiny operations, but every single one follows the same pattern we just saw. Now comes the key question. If we nudge x by a tiny amount, how much does the final output b change? Let's look at our graph again, with all the forward values in place. We can answer this by asking each node a simpler question. How sensitive is your output to your input? Start at the multiplication node. B equals a times z. If a increases by 1, b increases by z, which is 4. We write this as partial b partial a equals 4. Now look at the addition node. A equals x plus y. If x increases by 1, a increases by exactly 1. So partial of partial x equals 1. Here's the beautiful part, the chain rule. To find how x affects b, we simply multiply these local derivatives together. Partial b partial x equals partial b partial a times partial of partial x. That's 4 times 1, which equals 4. Let's verify. If we increase x from 2 to 3, the output changes from 20 to 24, a change of exactly 4. The chain rule got it right. This is the core insight. Each node only needs to know its local relationship with its neighbors. The chain rule multiplies these local rates together to compute the global sensitivity. Now let's run the backward pass. Here's our graph again with all the forward values. But this time we add a loss function. The loss is L equals b minus 16 squared, where 16 is our target. Since b is 20, L equals 20 minus 16 squared, which is 4 squared 16. The backward pass starts at the loss. We ask, how sensitive is the loss to b? The derivative of L with respect to b is 2 times b minus target. That's 2 times 4, which equals 8. Our first gradient flows backward. Next, the gradient flows from b to a. We multiply partial L partial b, which is 8, times partial b partial a, which is z equals 4. 8 times 4 gives us 32. From a, the gradient splits to both inputs. Since a equals x plus y, partial a partial x and partial of partial y are both 1. So both x and y receive a gradient of 32. What about z? The gradient takes a different path, directly from b. Partial b partial z equals a, which is 5. So partial L partial z equals 8 times 5, which is 40. And there it is. Every input now knows its gradient. Blue values flow forward, red gradients flow backward. This is the backward pass. So we've seen how backpropagation works, but why is it so important? Let's compare two approaches to computing gradients. The naive way. For each parameter, nudge it slightly, run a full forward pass, and measure how the loss changes. If your network has 100 parameters, that's 100 separate forward passes, one pass per parameter. The cost scales linearly with the number of parameters. Backpropagation does something radically different. One forward pass computes all the values. One backward pass computes all the gradients. Two passes. That's it. Every single gradient computed simultaneously. For 100 parameters, the naive approach needs 100 forward passes. Backpropagation needs just 2. The secret is dynamic programming. When a gradient flows backward through the graph, each intermediate result is computed once and reused by every downstream path. No wasted computation. Now scale this up. GPT-4 has about 1.8 trillion parameters. The naive approach would need 1.8 trillion forward passes. Backpropagation, still just 2. That is nearly a trillion times faster. Without backpropagation, training modern AI would be completely impossible. Everything we've seen so far used a tiny graph with just a few nodes, but the exact same process works on a real neural network. Here's a simple network: 2 inputs, 3 hidden neurons with ReLU activation, and 1 output. Every connection carries a weight. Phase 1, the forward pass. Data flows from input through the hidden layer to the output. At each neuron, inputs are multiplied by weights, summed, and passed through ReLU. Phase 2, the backward pass. The error signal propagates backward through every connection. Each weight learns its gradient, exactly how much it contributed to the error. Phase 3, update the weights. This is where episode 2's gradient descent returns. Each weight takes a small step in the direction that reduces the loss. Backpropagation tells us which direction to step. Gradient descent tells us how far. And then we repeat: forward, backward, update. Thousands, millions, sometimes billions of times. That is how neural networks learn. Let's step back and see the big picture. Training an AI model follows a single repeating loop. First, input data enters the network. The forward pass produces a prediction. We compute the loss, how wrong the prediction was. Then backpropagation computes the gradients. And finally, gradient descent updates the weights. Then we loop back to the beginning with the next batch of data. This episode gave us step 4, backpropagation. It computes every gradient the network needs. Episode 2 gave us step 5, gradient descent. It takes the gradients that backpropagation computed and uses them to update every weight. And episode 3's Bayesian thinking appears here too. Weight decay, also called L2 regularization, is mathematically equivalent to placing a Gaussian prior on the weights. Bayes' theorem is hidden inside the update step. GPT-4 runs this loop on 1.8 trillion parameters, processing trillions of tokens. Every single training step is one revolution of this cycle. Let's bring it all together. Backpropagation is built on 2 ideas: the chain rule from calculus, which multiplies local derivatives along each path, and dynamic programming, which computes each intermediate gradient once and reuses it everywhere. The result is a 3-phase cycle. Forward, compute all values from input to output. Backward, propagate all gradients from output to input. Update, gradient descent adjusts every weight. In episode 1, we learned how AI represents the world as vectors and matrices. In episode 2, we learned how AI improves by descending through a mathematical landscape. In episode 3, we learned how AI handles uncertainty with Bayes' theorem. And today, we learned how AI learns from its mistakes by sending error signals backward through billions of connections. In episode 5, we'll discover how AI makes decisions, softmax and cross-entropy, the mathematics of choosing the next word.